First of all, wish all of you happy Teachers Day. So the today's highlight point of FDP is trends and research in hydrogen and fuel cell. So I guess our today's session leaders are here. Firstly, I would like to introduce today's guest, Dr. Dadasaheb Shendage sir. Welcome, sir. Associate Director, Technical H2E Power System Private Limited. So firstly, I would just introduce briefly. So work as an lecturer during 2005 to 2006 in KJ Somaya College of Engineering. During 2012 to 14, work as an senior manager R&D in ATE Enterprises Private Limited India. So I have 11 years of hands-on technical experience in thermal engineering. Also, sir has experience in product design and development of modeling tools. So during 2016 to 19, Sir worked as a senior project research scientist in IIT Bombay. Also, Sir also play role as an vice president and senior vice president in innovation and product development. So currently working as an associate director in H2E Power System Private Limited, India. Warmly welcome, sir. We all are grateful to listening you, and it's opportunity to all of us to follow you. So I humble request to you, sir. Please start your session.
Thank you. Am I audible?
Yes, sir. Yes, sir. Please start your session.
Can you see my slide now? I'm at slide number 1.
Yes, sir. Yes, sir.
Yes. So you have already covered about 4 days now about this hydrogen and fuel cell, right?
Yes, sir.
So before talking about hydrogen fuel cell, its R&D, our experience. So I will also brief in 3-4 minutes our company, what we do, and I will share our project experience and everything. So before that, can I know someone can brief me what is the background of the audience? So are there any student or faculty from which branch, or there are some faculty from science background or engineering background? Can anyone brief me about the audience, please?
So actually, all of them are engineering faculty, also
Okay.
for general department faculties. So
Yes.
your session will be helpful for all of us, sir.
Okay. Got it. Got it. Uh, So now, can before going ahead, can you give me 4-5 questions that you want to interested from audience or all faculties? That this is hydrogen domain, and I will try to address during my session that answers. So any questions that hindering why hydrogen safety related or anything, any questions? So I would like to listen that before I start.
So my question is to what will happen in nowadays for research in hydrogen or the fuel
Okay,
cells?
research in hydrogen. Your question is what is opportunity in research in hydrogen, right?
Yes, sir. Yes, sir.
Yes. Okay. Okay. Research in hydrogen. Where is the opportunity to research, right? Got it. Any other question? In hydrogen field, yeah. What you want to know about hydrogen? Yeah, please. Hmm.
Hello,
Yes, sir.
this is Dr. Kulkarni.
Yes, sir.
What is the approximate timeline to establish the entire infrastructure required to get this hydrogen fuel into real time in
No.
India, of course?
So no. There is one question might be. we are installing hydrogen plant, let us say 100 kg per hour, 200 kg, that is technical specific. And I can give you the hypothesis, what we are expecting. Like as a solar PV, you can say in 2010 or 2000, 2010 and 2020 and 2025. Now solar PV cost is 14, 15 rupees per watt. In 2010 or 2000, in that decade, it was 800, 1000, even 2000 rupees per watt. 2000 to, let us say, 20 rupees or 15 rupees. So there is 100 in 25 years. The cost has reduced by 25 times or 20 times. You are getting it. So I got your question. Your question is what I see the future of hydrogen infrastructure and how it will be. Right? Am I right? That is your question.
Yes, yes, yes. To
Okay.
get an alternative to regular routine current, whatever petrol-based systems and other systems.
Got it, sir. Got it. Got it. Alternative solution. Okay, sir. Got it. Any other question before I start? Uh, got it. Electrochemical. So that Faraday's law and everything. Okay. So you want to know what is the calculation procedure to calculate the hydrogen generated in electrochemical, right? Yeah, I will give you numbers because that will be 1, 2 or 3 hours lecture will be there to get and to clear the fundamental. But I will try in 5 to 6 minutes to discuss how we measure and what are the industrial practices, and I will give you the approach. But for detailed calculations, it is 2 hours, 3 hours journey. But I got your questions. It will be addressed. Okay, sir. Electrochemical hydrogen, you can say quantification, right? What is the electricity, how much hydrogen it will be generated, and that. Okay, got it.
Hello,
Anything?
sir.
Yes, sir.
Sir, this is SM Chaudhary. I want to know what are the key objectives of India's national green hydrogen mission, and in what way it will be aligned with global hydrogen initiatives, and
Got it.
is the Indian government, planning for the balancing investment in hydrogen
Yeah.
with existing the renewable energy sectors like solar,
Yes.
wind? That I want to
Got
know.
it. Very nice questions. So for audience, what I will say, share, I will share from data also, and many things will be my personal opinion. I have listened directly, indirectly with authorities at different conferences, and their personal opinion. So don't go by that. Whatever I am saying, that is the final. Whatever my opinion or approach, right? But whatever I am showing these slides or authentic information, there I am also giving reference, because what I am saying, as the international or global politics is changing, the problem definition is changing, right? And we are closely in this business, so we know how it is changing. One decision that when Trump said that there is no CO2 climate change like that, and we will focus on fossil fuel. This one sentence has changed many projects vision. You are getting the point. So what will I will be share that need not to be true, but I will give our basis, whatever we are thinking on, and this thought process is being evolved year by year, month by month. You are getting it. It will be just purely I am sharing my experience with you. I will share. Are you aligned with it, sir? Please take it as just opinion at many places. When you, subjective type questions will be there. I got your question, sir. Next, any question, further question? I got your SF Chowgule's question about Indian. Please. No. Got it. Electrical batteries and solar energy. Okay. Got it. Got it. I have some enough material now. So I will stop to take the questions. But what I will tell now, if I have not something addressed at the last or I some forget, you can, if I forgot, you can remember me to address it. Sure. Can I start now? Yes, sir. Yeah. So I am speaking. I am also working with associate as associate director from in H2E Power Systems Private Limited since last 7-8 years, and I am doctorate from IIT Bombay in energy engineering, and my background is mechanical. So we have developed Stirling engine there in 4-5 years. Stirling engine, which is using working fluid as a hydrogen, and it will take waste heat and it will produce electricity. Or that was my background. Then I worked in solar concentrator. So at that time, solar PV was rising up, but solar concentrator had age. So you will get steam out of it, and we have installed some plant in laundries also. That is my background. But today's topic is related to hydrogen. These are the direct our experience from site, right? And you can correlate with it. So this company is backed by Adar Poonawalla Group. You can see this is Adar Poonawalla Group Serum Institute जिन्होंने कोविड वैक्सीनेशन डेवलप किया था. And this is our founder member, owner of the company, Siddharth Mayur. He is from Jain Irrigation Group. So this company is backed by Serum Institute of India. Major shares are Serum Institute, and also backed by Jain Irrigation also. So what we take in pride that we have developed indigenous first at HPCL Bangalore R&D Center, first solid oxide electrolyzer. I will come up to what is electrolyzer and everything. But we have successfully demonstrated, installed solid oxide electrolyzer in Bangalore, and it is producing half a kg per hour hydrogen, and it is operating since more than 6,000 hours now. Of course, journey was not too smooth, but it is indigenous and it is working as we expect, and it is half a kg per hour, and it is also safety approved. Then also our team, we are 48 people here, about 5 people are doctorate, and also 30-35 engineers in overall. So we have also developed hydrogen bus. We converted electrical bus 9 meter long into hydrogen fueled bus. So where to we keep fuel cell. We have also worked closely with ARAI, its safety, where to put type 3 cylinders at 350 bar and everything. So that is our competency that we have delivered. So we have delivered about 28-30 projects in last 7-8 years. So the first question is National Green Hydrogen Mission, right? So expected deliverables, why it is important for National Green Hydrogen Mission for India. And there will be about 8 lakh crore investment, 6 lakh jobs that we are looking for. So how it will be, you can correlate. So can you, I will go to the basic electrolyzer now, hydrogen generation. So I think this is a critical slide. One should really appreciate it. So we'll spend 2-3 minutes more. But if it is clear, then next journey will be really smooth. So can you see the temperature here? X-axis is the temperature. My cursor, you can see my cursor, right? Hello? Yes. So you can say X-axis 0 to 900 degrees Celsius. So please bear with me. I am asking again because I am not professional teacher or something. But so I am asking to just ensure that I am audible and I am connected. Okay, please bear me. Specific stack energy demand is y-axis, that is kWh per meter cube of hydrogen. This can be also converted into kWh, electricity required to make 1 kg of hydrogen. So in meter cube, in volume, or in mass basis, we can see. So now you can say this is the 100 degrees Celsius. And you can say this delta G, electrical energy required to break the hydrogen bond. Water is H2O. Volume wise, we have 66%, 66.6% hydrogen is there. Hydrogen 1 kg in 9 kg of water. That is theoretically available hydrogen. Now, if anyone says that I can produce 1 kg hydrogen on less than 9 kg water by consuming less than 9 kg water, there is something false commitment, or something other reaction is happening where hydrogen moles are coming. So now again here, so you have to focus on this delta G. So there are some commercial technologies available now that works less than 100 degrees Celsius, like as a PAIN, alkaline, or you can say AMC technology, right? So their electrolyte is less than 100 degrees Celsius. Obviously, electricity required to break the bond at ambient will be much higher. How much? It might be 50 units of electricity, 60 units of electricity to make 1 kg of hydrogen and to break 9 liter of water. At 800 degrees Celsius, you can say there is significant reduction in the delta G, electrical energy, you can say gives free energy. To activate and to break the bond, the electricity required at higher temperature will be much less. So what it says, theoretically, I had never experienced it. Theoretically, people are saying at 2400 degrees Celsius, at certain pressure, atoms will split at no delta G, no activation energy. That is theoretical limit. If we heat at certain pressure, more than 2400 degrees Celsius, it will separate. That is theory says. What does it mean? As temperature increases, there is less electrical energy required to break the bond. Now there is also, when you are making electrical energy, there will be I square R loss in every system. So this shows Q thermal energy. So you can say I square R loss or efficiency in this technology is much higher. So inefficient are there. But here, the thermal energy produced due to I square R loss or something else. So net electricity at 800 might be this, let us say 100 kilowatt, and 75 kilowatt might be the your net electricity used for delta G to break the bond, and 25 kilowatt is used as I square R loss. But to 800 degrees Celsius, when you are maintaining 800 degrees Celsius temperature, then it is called thermoneutral voltage. Whatever you are generating I square R, it is sufficient to manage that 800 degrees Celsius. So this is not waste, because we have to maintain 800 degrees Celsius temperature. But in low temperature, what you want to do, you are using delta G and there is high I square R loss or the heat available. So you have to provide cooling here. So basic difference between higher temperature and lower temperature electrolyzers is, here one additional balance of plant, BOP, will come into the picture, that is cooling tower or cooling heat exchanger. Something extra you will require by some means to remove the heat. But here you can say there is no certain feature is required. If you thermally balanced, this heat can be utilized to maintain that 800 degrees Celsius temperature. Are you with me? Any question till now? Hello, sir. Any
No, sir, no, sir.
No, sir. Okay.
Please continue.
Yeah, please. Thank you. So this is called 800 degrees Celsius is high temperature SOEC technology. This is PAIN alkaline technology. So normally commercially available, there might be 7-8 you can say technologies in the market, but commercially available and you can say matured TRL 8, TRL 9 level are these four: alkaline, PAIN, and AEM. Alkaline is more mature. Since 4 or 5 decades, that technology is available. So these three technologies work less than 100 degrees Celsius, up to 80, 90 degrees Celsius. But solid oxide operates 600 to 800. So we are working with 800 degrees Celsius temperature. The beauty is, you to produce 1 kg of hydrogen, you will require less energy. Let us say average it will be 35 units, but here average will be about 60 units. So there is chance that to produce 1 kg of hydrogen, you will require 50% more energy than SOEC. To produce 1 kg of hydrogen, you will require 35 to 40, let us say 40, and you will require here about 60 units. So 50% more electricity is required than SOEC to produce hydrogen at low temperature. So hydrogen cost, how you will calculate 1 kg of hydrogen cost? The one of the critical parameter that differs 70%. 70% contribution is electricity cost or OPEX cost. So OPEX cost is electricity required. Suppose you are requiring 60 units of electricity to produce 1 kg hydrogen. So the cost will be, of course, hydrogen produced cost will be 300 rupees. If per unit cost is 5 rupees. If per unit cost is, let us say, 2 rupees, and you are consuming 60 units to produce 1 kg hydrogen, so OPEX will be 120 rupees plus capex or else levelized cost of hydrogen and everything. So, are you getting the importance of electricity consumed in the cost of hydrogen? Are you there? Are you any question? Because to go further now, this should be clear. So what I want to conclude from here, the electricity consumed is very critical in the hydrogen cost. And at SOEC, will require much less electricity, OPEX, to produce 1 kg of hydrogen. Now, how it works electrochemically, water comes, and the theory, YouTube lectures from IIT professors, basic chemistry is available. So you can go for the basic to understand proton exchange, alkaline, its membrane, its material, it is naphthalene or zircon, cathode material, its nickel plating, its voltage, higher voltage or lower voltage. So electrical efficiency, it is everything is given in the. There are good notebooks, give good YouTube videos of IIT professors like as a Pratibha Sharma. I think Prakash Goswami is from IIT Kharagpur, ISC Bangalore. So there are lectures. So today we'll not go in deep with the basic of this. Why 4H, what is the Nafion property, what is the electrical conductivity or ionic conductivity, what will happen. That is available in the literature. So I will present our stand from commercial or industrial perspective. Any question on this slide? Yes, sir. Are you clear? No questions. Yes, yes. Right. So here the beauty of solid oxide electrolyzer is we are using no noble material. It's a nickel or you can say cobalt is the normal material. But here pain you have to use from platinum, right? That is that if platinum is critical material or iridium oxide is critical material. So the cost of pain will be always dependent on material cost, inflation and availability. So for my case, or our understanding is as a H2E power, we are focusing on a solid oxide electrolyzer because the available material, required material, and though it is efficient, required material is available in India, abundant. It requires iron, it requires cobalt, and somewhat nickel. For alkaline, so there is, you can say, zircon membrane is there. Apart from that, nickel mesh and everything is also possible. So this is most mature technology, alkaline. So we are working. We got the order 1 megawatt, 1.2 megawatt, 3 orders. One is Rajasthan, one is Himachal Pradesh, and now it will be start in December end, and one will start at April 2026. So let understand my perspective as per definition of what is gray hydrogen and green hydrogen, so that again I can correlate it with electricity. So you might gone through this since you are 4 days in this business. You are listening. You know the gray hydrogen and what is green hydrogen. So let us say understand in Indian context what is the definition of you can say green hydrogen. So what we follow, or rather I recommend, when you have to define this something about green hydrogen norms or everything, so we should follow MNRE. And all these rules and material is available in Ministry of New and Renewable Energy website, and they have defined what is green hydrogen. All right, 1 minute. Sir. So definition is very critical. Listen, including water treatment, electrolysis, gas purification, drying and compression of hydrogen of not more than 2 kg CO2 equivalent to kg per hydrogen, taken as an average over the last 12-month period. So it is average figure at least for over the last 12-month period. You should not produce at any level, electricity generation, drying, purification, everywhere. Per kg hydrogen, we should not produce 2 kg of CO2. If you use solar PV contributes 0.4 to 0.5 kg of CO2 equivalent per kg of hydrogen. Suppose if you can make 2 kg of CO2 or less than that, then it is called green hydrogen as of definition. This definition might shift after 3 years or 4 years. This might be 2 kg might become 1.5 kg or 1 kg. Right? It will never increase now. But this definition in 2030 might be 1 kg or 1.5 kg CO2 equivalent per kg of hydrogen. As of now, we have to prove less than 2 kg of CO2 equivalent to say we are producing green hydrogen. So now you can say gray hydrogen. You are using natural gas, and 1 kg of to produce 1 kg of gray hydrogen, you are emitting 9 kg of CO2. So it is not gray hydrogen. But if you are using natural gas, hydrogen, and you are capturing CO2, but it is you are storing somewhere, but it is here you are producing 9 kg CO2. Here you are producing net emitting very less. Split natural gas into CO2 and hydrogen, CO2 reused and stored. So it is called blue hydrogen. These are the definitions from MNRE, right? And green hydrogen is you are using green electricity and you are getting hydrogen. However, by some means, you are using some fossil fuel, let us say theoretically, and you are producing hydrogen without any emitting any CO2 to the atmosphere. Can we call it as green hydrogen? As per definition, I will again repeat, green hydrogen standard for India specifies threshold of 2 kg of CO2 equivalent and K per kg of hydrogen as a 12-month average. If you are using water, hydro energy or wind energy, solar energy, so it is green electricity and you are producing hydrogen. My question to dwell, to think is, if you are using fossil fuel and I am not emitting any CO2 to the atmosphere and I am producing hydrogen and my hydrogen is now emission, I am emitting less than 2 kg of CO2, can I call green hydrogen? That we will discuss. Now we will listen about what is our philosophy or people are thinking about green steel. So now there is philosophy. If you are green steel, there is some, you can say, in policy, there is some incentives. Let us say first year 50 rupees per kg, in second year 40 rupees per kg, or 30 rupees per kg might be the incentives for green steel, using green steel. What is green steel? So you can say any green steel should consume less than 2.2 tons of CO2 equivalent per ton of finished steel. So 1 kg स्टील बनाने के लिए कम से कम आपको 1 kg CO2 इक्विवेलेंट है, तो 2.2 CO2 इक्विवेलेंट लगता है. So then it is any green steel. 3-star green steel rated steel is it is 2.20 to 2.22 tons of CO2 equivalent per ton of finished steel. And 5-star green steel, you can say it should produce or it should emit less than 1.6 tons of CO2 equivalent per tons of finished steel. Right? So that is definition of you can say 5-star, 4-star, and there are other incentives. If you are using 5-star green steels, and there is different incentives in the policies. Of course, this 5-star green steel as of now it is expensive, so this incentive is required. Any steel having an emission higher than 2.2 tons of CO2 per tons of fine finished steel will not be considered as a green steel. Right? It is very clear. This threshold limit for defining the categories will be reviewed every 3 years. ये जो है figures 2.2 to 1.6, 1.6 that will be reviewed by every 3 years. And like as BS6, BS4, BS5, how it evolved, sure it will go down. 2.2 might becomes 1.2 or 1.5 after 10 years or 12 years. This 1.6 might become 0.6. So, but every 3 years, these figures has been reviewed. So it is about green steel. So now, why we believe this is a levelized cost of green hydrogen? So you can say in India, can you see here 0.76? So this is the data in 2020 authority. This is authorized data by PTX Hub. This is the Indigenous Institute, GIZ. It is also government institute, and IKI. It is international institute. So the three teams work together, and this is the information from their report. So let's understand that what this report says. If we are going for mass production, so the levelized cost of hydrogen, you can say, is $0.76. So let us say $1 is 100 rupees for calculation purpose. So what this graph means, there is potential that we will get 1 kg of hydrogen if everything is in the mass scale, 76 rupees per kg of hydrogen. आप समझ लेना कि CNG का कॉस्ट है अभी 90 rupees per kg. CNG and hydrogen, CNG will have calorific value up to 40 to 50 megajoule per kg, and hydrogen has a 120 megajoule per kg. It is about 3 times more. So roughly you can consider 3 times more. You are getting hydrogen at 76-80 rupees at certain conditions, right? When it will be going big mass production, and this is hypothesis. And you are getting CNG at that period, let us say 2030 or 2035. You are getting your natural gas. Abhi 90 rupees, it might be 200 rupees at that time. And the calorific value of CNG is about 3 times less than hydrogen. So if अभी consider कर रहे हैं तो ये 76 rupees पकड़ा, तो what we are saying 25-30 rupees को 1 kg CNG मिल रहा है equivalent. Are you with me? What I want to make the point? Why hydrogen is a critical? Yes. So what we are saying, NG equivalent to 25 rupees. And in 2035, this NG might be 600 rupees or 800 rupees per kg. We don't know. It is fossil. It is limited. But now, if hydrogen as a fuel, if we go for, and you can see here, what hydrogen as a fuel, what India need. There is sufficient solar radiation available. There is sufficient water available here, right? And then then it is possible. So for Indian context, we can be you can say fuel producing country. So whatever we are doing from Russia now, oil India, if we have to go for 5 trillion economy, now we are 1.2, 1.5, 3 times, 4 times we have to increase our GDP. Then what will happen? We will need 3 to 4 times energy. So whatever solar we are doing, whatever diesel, petrol or fossil fuel will require, everyone will have a place. No one will destroy or no, it will not, we can say it will not be vanished from Indian economy. But to meet 3 times energy requirement in future, 4 times energy requirement in future, hydrogen is promising fuel for India because we have sea water, enough sea coast. तीनों साइड से हमारे सी कोस्ट है, and there is sufficient solar radiation. तो पानी है और इलेक्ट्रिसिटी है, तो हमें हाइड्रोजन बना सकते हैं, और इट विल बी डिसेंट्रलाइज बेसिस प्रोड्यूस and within 500 kilometer, 400 kilometer, use it. Right? So that might be the thought process of the government. To be, our goal is in 2047, we have to want to be 2047 when we will complete 100 years of independence. Energy secure. What does it mean? Energy secure. हम हमारा खुद का इतना एटलीस्ट एनर्जी हम खुद बना दे. तो मैंने एक कॉन्फ्रेंस में सुना था कि व्हाट यूर अब सपोज हमारा गेहूं है 40 रुपीज पर केजी वीट, तो 8 to 10 rupees we are giving abroad or during oil cost. How? So whatever tractor diesel will require or diesel we are consuming, the farmer using mobile or electricity for water pumping, concluding everything. So for any product, 8 to 10 rupees, any, so about 15 to 20% has energy cost. मोटा मोटी बोल रहा हूँ मैं. तो आपको जो भी गेहूं है, तो गेहूं बनाने के लिए आपको 10 रुपीज का एनर्जी लग रहा है. इफ इट इज कमिंग फ्रॉम इलेक्ट्रिसिटी, इफ देयर इज डीजल कॉस्ट इज ट्वाइस, लेट अस से 40 रुपीज का गेहूं है और मेरा 10 रुपये एनर्जी कॉस्ट है, बाय सम मीन्स माय डीजल कॉस्ट इज डबल्ड. indirectly my wheat will go to 40 rupees to 50 rupees because my energy cost is 10 rupees, that is becoming 20 rupees. So now my production cost might be selling cost might be 40 rupees to 50 rupees of wheat. So how the energy is playing in the role. So here, to have our own energy security, hydrogen is playing a great role because we have sufficient solar radiation, wind, and also hydro, and also we have sufficient water resource. Before going to next slide, any questions? Because I have answered one questions. Hydrogen generated, Indian green hydrogen mission, electrical solar energy. So any question on this slide too before going shifting to next topic? Any question? Okay. Okay. But am I audible? And it is yeah, yes. अभी हमारा थ्रेट क्या है? So why India, our research is needed, why people are funding, why this green hydrogen mission, why this well thought process efforts we are putting. So there is equipment called electrolyzer that will make, or alkaline electrolyzer that will make water into hydrogen. So you can say the per watt cost in 2021 in China to make that equipment was $0.3. In Western made or Europe, you can say cost is $2, $1.2. If we are going in this field in 2020, it is 0.3 per watt. Then when we will require the electrolyzer, obviously one will prefer China. So what will happen to make an energy security? We are giving chunk of money to China because it's really challenging to make electrolyzer, alkaline electrolyzer, less than $0.3. And now it is 2021 data, it is 2025. This might come as 0.2, 0.25. So you are getting the why indigenous, make in India is important. We want to go in hydrogen, but not by this route. Got message is clear? So the China cheaper raw materials and labor are available, higher factory utilization rates are there, 12 hours, 18 hours factories are working, lower spending on R&D and marketing, right? Lower spending compared to Western. India से ज़्यादा R&D करते हैं वो, but compared to USA or Europe, there's lower spending on the R&D and marketing. So then there are many technologies. If CO2 is there, so you can dump into the seabed or in the ground. So there are sequestration methodology. So we will not touch this technology as of now. Let's see hydrogen. Today we will focus on hydrogen only. So this is our plant installed in 2022. It is at Johrat, Assam, and it is producing 10 kg hydrogen per day capacity using AM technology, anion exchange membrane. So it will require about theoretically 9 liter, but practically 10 liter or 11 liter of water, which will produce 1 kg hydrogen, oxygen, and remaining will be electrolyte or water. So for 10 kg hydrogen, we are requiring about 80-90 kWh or kilowatt plant. And this hydrogen we are making, producing it, and there is natural gas line, and we are blending it. Blending means we are increasing its calorific value per mass basis. So suppose your calorific value is let us say 35 megajoule per kg, it might cost let us say 30 rupees per kg. If your calorific value is 30 rupees, so your cost of NG might be 18 rupees or 20 rupees. And if your calorific value is let us say 45 megajoule per kg, the cost might be 60 rupees or 50 rupees. But on mass basis, if you blend the hydrogen, so my gas whom I'm selling to 25 rupees or 30 rupees, that might I can sell at 35 or 48 rupees, because now my calorific value is increased. But I am generating this green hydrogen and I am blending it. This is one of the way. Second way, this blended gas they are using in their casket, or you can say their network, where industrial use for feedstock or cooking or heating. So if they're requiring in year 100 kg or 100 ton of natural gas, partially due to hydrogen, its consumption will reduce. It will come to 100 to 95 or 90. So that is the thought process. So we are blending. And third is, if this hydrogen is stored, you can see here hydrogen is stored, and we are supplying it to the hydrogen bus. So there is a forest called Green Belt hai udme Guwahati to Assam, Kaziranga forest. So they have planned to run it this bus on scheduled time from Johrat to Kaziranga, and it will again fill the hydrogen at Johrat. And there is green transportation or green you can say पर्यटन बोलते हैं ना, ग्रीन tourism. तो उसका वो पार्ट था. So they are making green hydrogen here, and there will be hydrogen bus. So this hydrogen is used for three purposes: hydrogen for bus, hydrogen for you can say cooking or blending, cooking, and hydrogen for their selling also, blended hydrogen. Before going, and we also operated it for 3 years. Now we got also renew contract to operate for 3 to 4 to 6 years, next 3 years. So any question on this slide? Audience, anyone is any question on this slide that is not understood, that is not addressed? ज़्यादा हो रहा है क्या? It is very low, or I'm telling you very basic, or very extremely high, or it is more industrial related? Can I get the feedback? Okay, I think there is no responsibility. Everything is okay. Okay, I will continue. Yes. So now, what we believe, as we discussed again, solid oxide electrolyzer will be more efficient, right? Here we can see 800 degrees Celsius. SOEC is taking much less energy. So we have developed our own solid oxide electrolyzer technology, right? So there is called component called stack. There is hot box, so it will insulate it. So there will be about 6 inch, about 150 thick insulation will be there around this stack. and you will provide a rectifier. There will be a rectifier, and we will provide DC voltage to the stack. Of course, it will convert from AC to DC. And the beauty of this is schematic. The SOSC technology, if you use steam, you will get hydrogen. If you use steam plus CO2, you can get syngas, hydrogen plus CO. And you can use Fischer-Tropsch reactor and you will get liquid fuel like as SF, sustainable aviation fuel. There will be one process that is Haber-Bosch process. That is not shown here. But you use steam plus air. Air means nitrogen. You will get here through Haber-Bosch process and SOSC, you will get ammonia. And it will be utilized in fertilizers. So this is one thing. Presently, we are a lot of dependent on fertilizers and ammonia on China, or you can say abroad, foreign countries. But we want to be indigenous on this ammonia. So there will be many tenders you can see on the ammonia. So this technology can give address product as ammonia, syngas, or hydrogen. So now you can say there is how it works. There is solar PV, there is you can say grid, and there is SOSC of you can say 20 kilowatt. And there is hot box to insulate it. So inside temperature will be about 800 degrees Celsius. Outside might be 2 or 3 degrees Celsius more than this ambient. So we are providing cathode air here. We are providing steam or water initially. Steam plus cathode air. There will be anode and cathode material. We are providing electricity here. And we will get hydrogen plus H2O initially. And that water vapors, we have to separate it and then you will get pure hydrogen. So this is the technology here. So there is no rare earth material required like as platinum or anything. So we take that hot box is indigenous. Yes, stack is made in Germany, but that is in our own company. That is called Empower. So we exist also in Germany and Switzerland. And hydrogen which is coming here, and whatever remaining oxygen that will be added into the air, and you will get oxy-rich air. So here air might be 18 to 20% oxygen, and here might be 35 to 40% oxygen in the air. So it is called oxy-rich air. And then if you are for SOSC, if you are using the waste heat as the input, then if you like it's very close to ice, then there is 100 degrees Celsius steam or 300 degrees Celsius theoretically required energy will be reduced. So at 800 degrees Celsius to break the ionic bond, or you can say to convert hydrogen and oxygen molecules separate it, theoretical energy required 26.6 units of electricity. As temperature decreases, this energy is going to increase high. What does it mean? Whatever steam at high temperature you will get, waste heat you will get, electricity required will be much more, much less, right? And then compressor and everything that you can see. So in electrolyzer, there will be some critical parts. So there will be electrical power, then there will be power supply, and for higher megawatt plant, this power transformer, let us say 1 megawatt transformer is there, rectifier is there, about 150 kilowatt in 1 megawatt will be the heat. So there then power system cooling will be coming to the picture, and for its process control and safety system will come into the picture. So it is called power control model. So this is one of the critical part of any plant. Then for SOSC, air is required, cathode air, to sweep the gas, whatever oxygen you will get in the cathode air, cathode stream, you have to sweep it. Then there is water required, and it will convert it into water, will be converted into the steam through the, you can say, steam generator. And there will be hydrogen bottle system and nitrogen. Nitrogen bottle system is for safety. Suppose there is leak, and then this nitrogen can go there and it can dilute hydrogen concentration in the pipeline. plant will be shut off. Still, hydrogen line will be on, and it will dilute the hydrogen concentration in the pipeline. Same for hydrogen bottle system. Initially, for inert gas to increase the life, we will require some hydrogen. So the hydrogen bottle system will be there, and it will be filled when plant is running. So it will consume about 0.5% whatever produce hydrogen, 0.5 or 0.2% in hydrogen bottle system. So then there is hydrogen compression system. Compressor will be there. Suppose you require 200 bar or 300 bar, 350 bar. Same quality of compressor will be there. माझा आवाज येतो का बाहेर? Then there will be SOC stack modules, hydrogen cooler will be there, hydrogen drying system will be there, purification system will be there. And there will be then hydrogen, wastewater, exhaust air. So any question on this block? Dear faculties, any question? Because I think your answer of R&D scope is everywhere. So I can see there is more than 100 problems that this slide addresses. Like as for electrical engineer, how our power supply system should be, its reliability, what is this ripple factor, how we will design, how the cooling system will be more effective, and how this interlocks will come to the safety perspective, because we are dealing with hydrogen. So development of rectifier, sizing of rectifier, its analysis, you can say power supply AC to DC conversion, or if we have solar PV megawatt plant, can we make a system सोलर से डीसी आ रहा है, अभी तो एसी बनाते हैं, बट डीसी आ रहा है और डायरेक्टली वी कैन यूज इन डीसी, समथिंग लाइक द डीसी डीसी कन्वर्टर. So there is many opportunities, many publications are coming in this area, and how the ripple factor is affecting on the hydrogen generation. So this there might be 10 to 12 burning areas here in the electrical power for electrolyzers. Is you are using thermistor based rectifier or IGBT or something called silicon carbide, very expensive. I have not seen silicon that carbide they say, but they are saying very effective, that are 6 to 7 times expensive. But we are using IGBT or thyristor based rectifiers. So for electrical departments, I think there is huge opportunity to contribute in different level of plants. Then there is water, steam generator, steam generation at 800, 700 degrees Celsius to heating it. And it's DI water plant, so how we can reduce the energy, electricity. That is the opportunity here. You can say here, emergency hydrogen vent. What should be the vent design? At what height? Can you simulate it? So CFD people come into the picture. If what will happen if I release the hydrogen, and let us say on 2 kilometer, hydrogen is very light and it will go very fast in the atmosphere to mix it. And there is aeroplane is coming, let us say 2 or 3 kilometers, and there is some hot part of aeroplane, and this hydrogen goes there, and bad luck it matches. So what will happen to aeroplane? So what is the minimum hydrogen that you can purge through the vent, so that situation will never come. So here computational fluid dynamics, or you can say softwares, ANSYS and everything, so that will come into the picture. So if you have to vent, you have to monitor the rate of the venting. Hydrogen compression. So it is not simple. The material selection, metallurgy will come into the picture. At 350 bar, 200 bar, why 200 bar, why 350 bar? What is type 3, type 4 cylinders? How we can reduce the cost? Which type of threads we should use? How we can prevent the leakages? So the many how we can reduce the cost. So many areas are opening. Okay, मुझे phone आ रहा है एक, but I am audible. It is not, the phone is not from audience now. Am I audible? Yeah. Okay. Does this topic seems interesting to you? So I can define more topic for R&D. Yeah, yes. Yeah. Yeah, because hydrogen and oxygen is flammable ना, and उसका flame नहीं दिखता है, right? So now we have to take care when we are making layout hydrogen plant. There should not be big transformer, or there should not be DG set, or there should not be diesel or petrol storage pump or petrol pump nearby, certain vicinity. So in factory layout, in refinery, you have to take care. It is not that chota in school or in colleges to demonstrate little hydrogen is something like that you can accept. But for megawatt levels, 20 megawatt, 100 megawatt, so you have to plan it. So what will be the expansion? What will be the future expansion? When you are putting 100 megawatt or bigger hydrogen plants, that means initially you are saying in future that you will not do these 10 things. Like there will be no petrol pump. There you will not storage the water or diesel or petrol or CNG. You are getting it. So for bigger plants, it is planning, future planning within 10 kilometer or within half a kilometer periphery. What is going to happen? That need to be decided. So there is SOSC stack modules. So how we can make stacks, how we can reduce the cost, how we can reduce the material, how can we can increase the production, reliability. Can we reuse it after 10 years, 20 years? Life of stack is there, and there are critical material, critical parts that can be reused. राइट हम टायर चेंज करते हैं लेकिन ड्रम नहीं चेंज करते और रिम नहीं चेंज करते अनलेस इट इज बेंट और लाइक दैट सो लाइक एज एसओएसी स्टैक में एक इंटरकनेक्ट करके पार्ट है क्रिटिकल उसमें क्रोमियम होता है क्रोमियम एंड आयरन but that we can use or retrofit after 20 years or 15 years. There is hydrogen cooling required because we will get high temperature hydrogen here. How to cool it, how to give the waste heat out of this. Then how to generate steam at 700, 600 degrees Celsius with controlled rate. How to measure it. Feed water treatment, or you can say water plant, DI water plant, ion exchange system. So all these are the topics. And everyone is working to reduce the cost, to make more efficient, more reliable. Right? So I will go to, and then bottle racks are there, electrolysis modules are there. So the same you can implement for low operating temperature. Some parts will be changed. There will be no steam generation, but there will be electrolyte circulation pump. So that will be there. But every parts to optimize, to design, to reduce the cost, to increase the reliability, there are huge opportunities. So I will share our thought process here. So this is made in India, SOEC. We have make hydrogen, and it is for producing about 5 nm cube, means about half a kg per hour. And we are also using compressor to make 3 bar G, but it is 30 millibar G. So I have changed it. And we have also published patents. We have total published 18 patents, Indian patents as an institute, as a company. Out of these, 2 patents are related to SOEC. So we have 5,000, 6,000 hours data. One patent is related to BOP, one patent is related to stack. So stack patent is granted, and before 2 years we have filed BOP patent, and it is in process of granting. We have submitted the FER, replied to FER, and this is the sample data we are taking. So we have 5,000, 6,000 hours, 2 systems data is with us. Third system we are building. So this is overall scheduling, you can say. This is water, air, this is pre-processing. Electricity, nitrogen, hydrogen will require. Pre-processing, steam generation, dam water plant. And this is post-processing. You will get air plus O2, H2O plus hydrogen. We have to dry it. Then we have to put into buffer tank. Then there will be a booster which will compress up to 10 bar G. Then 10 bar G go up to the 200 bar G. So compression, you can say buffer vessel design, it's drying, everywhere engineering is required and optimization will be required. And you are getting O2 enriched here. So you can say there is tree like as a one electrolyzer plant, let us say megawatt level, is like as a 100 or 200 big trees, forest is there. So impact is giving one green hydrogen plant is giving impact like as a one forest, because it is producing O2 enriched air, right? And here it is giving, you are getting oxygen 24 into 7, as you are getting hydrogen also, but you are getting oxygen also. There will be also some condensate you have to tackle. You can recirculate this, and there will be safety system, emergency vent, and everything that you need to address. So every aspect is now to for design, development, cost reduction, reliability, analysis. There is huge opportunity in every aspect, and the gas sensor to measure the hydrogen leak and its sensor, everything will be required. So now, the present issue is the cost of any plant. 10-15% cost is in instrumentation. Now you can see that I have to measure the purity of hydrogen. If I have to measure the 300 up to third digit, there are unique way. You cannot go for conductivity based purity measurement. So how I can measure which instrument? This cost, these are 3 lakh, 4 lakh, 5 lakh rupees costly imported items. And what we find out that we need some indigenous, reliable, low cost purity measurement sensors, right? And it is possible. But if that mass and indigenous development is done, then it is possible. So instead of 5 lakh rupees sensor, I can offer 25,000, 30,000 rupees sensor, and it is possible. So to development of sensor, and sensor will be used everywhere, in alkaline, in SOEC, and everywhere. So I will share the our journey of the SOEC development.
The person you have called is speaking.
Yes, sir. यस, हाँ सर, मैं एक मीटिंग में हूँ, मुझे आप इंट्रोड्यूस कर देंगे आप? हाँ हाँ, किधर से बात कर रहे हैं आप? किधर से? ओके ओके ओके। हाँ सर, मैं एक बार कॉल करके ऑनलाइन कॉन्फ्रेंस में आपको कॉल करता हूँ मैं सर। ओके सर, मैं कॉल करता हूँ आपको। ओके सर, ओके। Sorry, there was call. So this is our journey of electrolyzer. Are you with me till now? Any questions, audience, faculties? Are you with me? Any questions till now? No questions? Okay. So uh, now we will see different projects in hydrogen field. What we are doing, that is development of, now we are hydrogen fuel cell powered electric cargo. It is sponsored project. So can we make electrical vehicle or three-wheeler into hydrogen? So where we should put the hydrogen cylinders, how the balancing weight will be there, uh, what will be turning radius, and how will be refilling system, what will be safety. So many features we have to address if you have to make three-wheeler cargo project. Why need for electrification or hybridization, you can say. So upcoming CO2 reduction targets are 99 gram per kilometer. So there is way, if you have to go for petrol or diesel, then if we have to achieve this target, CO2 reduction targets per 99 gram per kilometer, then there is way, electrical way, or you can say hydrogen vehicles. So this is the main driving force why you are going for stringent emission norms of Euro 6 and beyond. And if you have to meet this CO2 reduction targets less than 99 gram per kilometer for three wheelers, then this is the technology. Yes, please. Yes. Okay. Okay. I will share again. Can you see? Can you see now? So what I'm saying, why three wheelers or four wheelers we are going for with hydrogen? One of the reasons. I'm not saying it will happen in 2 years or 3 years, but this is the vision for 2070 climate decarbonized India, right? And 2047 is energy independent area. So we have energy freedom, right? We will make our energy, we will produce our own energy. So the first now stringent emissions norms are coming for Euro 6 and beyond. Euro 7 might come, Euro 8 might come. Whatever CO2, CO, NOx, NO, that everything will come into picture. One of the target people are looking at upcoming CO2 reduction targets are 99 gram per kilometer. And now we want drastic change then. Whatever these rules are coming or stringent norms are coming that need to go, it is making to go in hybridization, like as electrical and hydrogen fuels, which do not produce CO2 equivalent emissions. So this is motor control, BLDC motor, and how what will be the voltage and currents will be there. So question about hybridized 1 meter. Yes. So one of the question was ki, what is the infrastructure alternative solutions and every will be there. So this is hypothesis I'm sharing with you. Now we'll go in deep. For just go through the calculation. Battery electrical vehicles. So this is not my analysis. This is a reputed place. I also given the source for this. So this renewable power is 100%. You are using battery charging, discharging. Net use is 69% in automobile. If you use electric motor, mechanical efficiency considering 95%. So if you are producing 100 watt, equivalent to 69 watt of mechanical power, mechanical work has been reaching to the wheels on the road. If you are making fuel cell with vehicles with hydrogen, So fuel cell efficiency is 60%, 55, 60%. You are making PV into 67% is the hydrogen generation, electrolyzer efficiency. It is reaching to 70, 75%. Now this 26 is going up to 35%. Third option is internal combustion engine with hydrogen, let us say. So you are using 100 watt, 100 watt, 100 watt. So what finally you are getting here is 30 watt, 13 watt. Here now 35 watt. That can go up to 70 watt. So this is the better route to utilize the energy, electrical vehicles. But what analysis shows, people believing that when vehicle size versus driving distance, if you have to go long, so if you are going 600, 700 kilometers per day, your running is much more and your vehicle size much more. Load carrying capacity is much more, like as trucks. So hydrogen will be most preferred because fuel cell cost is high for 200, 500 kilowatt. It is high, and also we require some space to accommodate the fuel cell. Sorry. So as vehicle size will increase and the utilization of vehicle per day is more than 500, 400 kilometer, 600 kilometer, then this is the sweet square for hydrogen. If you have using electricity, then your driving distance might be less than 100 kilometer per day, 150 kilometer per day, and the load will be much like traveling load, two person, four persons, but sorry, and you are ensuring that in majorly in city, you are ensuring that there is provision to charge the battery. Then four-wheelers or three-wheelers, or you can say auto rickshaws running on the electricity might be making sense. So this is the, you can say, an oil, biofuel, CNG, synthetic fuel will be in this between. So that is our people are sorry, people are looking for the application of vehicles. So at least next 40, 50 years, everything will be aligned. Petrol engine will be there, diesel engine will be there, CNG engines will be there. But electrical and hydrogen, you can say, for electrical vehicles, before 10 years, in 1000, you can say one or two electrical vehicles were there. As of now, you can find out in 100 vehicles, there are 3 to 10 electrical vehicles you can find it out. So slowly, what you want to say, suppose there are 1 lakh vehicles, diesel and petrol vehicles will be there, but the hydrogen vehicles now it is might be 1 or 2 in 1 lakh, or 10 in 1000 or 100. That ratio will increase. So, any question on this side? I think I am expecting some question on this side. Any question on this slide? Faculties or any opinion? You need not to be agree with me. Any other opinion? Shall I go ahead? Yeah. So what I see, there are, if we are to go for hydrogen fuel, there are majorly two technologies. One is IC engine, one is fuel cell, hydrogen IC engine. But there are some basic flaws in hydrogen IC engine. As per my information, there are 2 to 3 problems. People are claiming they have developed S2 IC engine for running for 4,000 hours, 5,000 hours. They are testing on the vehicles. But I am not aware that there are 3 to 4 problems, how they are solved. One is hydrogen embrittlement, the material selection, cylinder liner. What happens when you are shut down the hydrogen vehicle? When hydrogen and oxygen coming and it is burnt or exploded on the piston, it will generate some water. And that water might come into the mix with the oil. the oil properties might deviate. So the viscosity or that oiliness, lubrication point of view, after 4,000, after 40,000 hours, that might be need to be addressed. So one is the hydrogen embezzlement. Second is the how we are handling the water generated in the crankcase. Third is the temperature is very high because we are burning hydrogen. And as 1000 1100 degrees Celsius may cross, then nitrogen oxides NOx might come into the picture. So there are 2 to 3 issues that are challenging to meet that stringent work, safety, and everything. So IC engine, but for Indian context, if we got a reliable hydrogen IC engine, people call H2 ICE, will be the great breakthrough for Indian context. PEM fuel cell much more efficient, but no one, though they claim it works for 50,000 hours, 1 lakh hours, we have worked with 5, 6 dealers, or you can say manufacturer of PEM fuel cell. But I see literally practically after 5,000 hours, really it can work the way the way it should work is really doubtful. But people are putting efforts in fuel cell also, H2IC engine also. Both topics are emerging and a huge opportunity to do the research. Now you can say there are about 500 crore proposals, R&D proposals. Now currently Eminari call is also there. So the India as India, they are defining the problem R&D projects in hydrogen domain. So I have taken the one snapshot from one of the roadmap for green hydrogen in ecosystem. This is an open loop and this is authorized from Hydrogen Mission Authority. You can see the R&D focus as a present. Development of high efficiency electrolyzers targeting 1.6 volt. Presently, many electrolyzers are consuming 1.82 volt per cell to make 1.6 volt or less than that. Development of biomass-based gasifier reformer for hydrogen generation with target yield of hydrogen per unit of biomass based on the Indian scenario. There are high temperature material, configuration of gas turbine, blending, development of platform mountable methanol, very low platinum electrocatalyst tolerant to pollutant air to develop PMFC for that. Development of high efficiency safe hydrogen high pressure compressor technology. So particularly compressor technology need to be fine-tuned for hydrogen safety and hydrogen as a fluid. Development of pilot SOFC stacks for coupling with gasifiers. Development of softwares if we are getting the solar PV, wind, and electrolyzer, how we will size it. That simulation software scope is also there. Then R&D priorities, project with midterm of 0 to 8 years, impact horizon, demonstration actions for encouraging startups and industry. Are you with me on this slide? Any question on this slide, sir? कोई किसी का प्रॉब्लम है क्या? Suppose they want to start R&D or they are doing R&D. If you know that you are already at one good TRL level or you are doing one interesting research in any topic, you can share in half a minute or 1 minute so that I will also come to know. कोई काम कर रहा है क्या कोई फैकल्टी इस फील्ड में? H2 IC इंजन में कोई काम कर रहा है क्या? Anyone is working in H2 IC engine? Okay, sir. I will go for. So can we take 5 minute break? थोड़ा सा, हाँ, 5 minutes. So when we will join, you can say new applications are coming in data centers. And each data center is minimum data center is up to 100 kilowatt or 60 megawatt or 100 megawatt or 300, 500 megawatt. So it is like a small village or some small taluka or district place. So how to ensure that 24/7 electricity, reliable electricity? So one of the solution is fuel cell, solid oxide fuel cell for data centers. So VSOFC is becoming globally one of the hot topic. And we have also product solid oxide fuel cell. So I will share and next 10-15 minutes I will discuss about solid oxide fuel cell. Can you see my slide? SOFC, solid oxide fuel cell. Yes. So let's understand its chemistry, its working. Right? So we have discussed SOEC, solid oxide electrolyzer. When we will produce, we are giving electricity and steam or water, and we are getting hydrogen. But SOFC, you can give H2 plus CO or hydrogen or syngas, H2 plus CO as an input, and you will get electricity as output, and output will be H2 become H2O, CO will become CO2, correct? But that CO2 might be, for methane, that might be 3 or 4 times less than the IC engine per kW, because it is SOFC is more efficient than IC engine. You can say for steam methane reformation, when you will provide CH4 and it will convert into H2 plus CO, so efficiency can go up to 60%, depending on electrolyte supported, anode supported, right? So if it is so efficient, whatever small engines, 5 kilowatt, 4 kilowatt, in 5 years, 6 years span, the overall efficiency will go up to 18-20%. And here you are getting 60%, so 3 times more. So CO2 produced per kg of hydrogen per kilowatt will be much less. So you can see in this material, so there is stacks or cells. You can see number of cells will determine the fuel cell stack capacity. We have our one stack that is 30 watt per cell, SOFC stack. It can be utilized in SOFC mode and SOEC mode also. Electrolyte, which shows the ionic conductivity, is the critical part. And its rating is defined by this active area, 127 cm square. It is overlapping area. Minimum overlapping area, that is 127 cm square, which will determine the current. Because current density will be 0.4, 0.5 ampere per cm square, and that area will decide how much current it can take. So open circuit voltage, operating voltage, and that are critical parameters in the fuel cell. So this is our product. You can visit Pune and you can see also this is 1.5 kilowatt, and we have supplied this to IOCL Delhi and also Makum, Assam Makum site. So they are using natural gas as input and they are getting electricity as output. So here you can say it is cathode, you can say CPOX, cathodic partial oxidation. We are using the electrical efficiency, we are getting 40-45%, though here it written 40%, 40-44% we have demonstrated. So this is fuel utilized, savings versatile, so we'll discuss this. So this is traditional materials in SOFC. You can say for electrolyte, it should be highly ionic conductive material should be there. Its density should be high, right? And it will only transfer ions, like as oxygen ions. So it will not transfer hydrogen or hydrogen compounds. Same, there will be cathode material will be there, large reaction field, oxygen absorption, ionization will happen. Numerous paths for electron and ion conduction will be there. Porosity is required, appropriate porosity will be there. Okay. So there is interconnect, like as material will be LASR or LACA, CrO2. So this is also area to research, metallurgical point of view, which composition, how should process, at what pressure you should make this interconnect. Will the thermal, what will be the thermal expansion after making it at 800 degrees Celsius? Many parameters will be there. So materials is one of the area to research, to experiment. And there also degradation, you can say. Okay, after 8,000 hours or 80,000 hours, how this fuel cell will act, right? And then levelized cost, operating cost, capex that need to be addressed. The critical point is the heart of is the electrolyte. So you know the ionic conductivity of electrolyte is directly proportional to temperature. As temperature increases, 800 degrees Celsius, you can say oxygen ions transferring will be much more than at 600. So now the practical limitation is that 1000 it will operate like as a 2 to 8, 4 times performance might improve. But the materials available, reliability, that restricts us to go beyond 800 degrees Celsius. There are some experimental results up to 1000 degrees Celsius. But ionic conductivity, you can say 2 to it is going to 8. The performance might improve. But do we have some metallurgy, which will work for 50,000 60,000 hours and it will be stand continuously at 1000 degrees Celsius. So, but 600 to 800 degrees Celsius is where we are working, and we have stack with 800 plus minus 50 degrees Celsius. So certain experiments have been done in the literature, you can say. We also did, but this graph is from literature. So this is 850 degrees Celsius initial experiment. So this is the, you can say, current density a milliampere per cm square, and there is voltage you can get. So you can say at 150 watt 200 milliampere per cm square, you can say 150. So you will get at higher voltage you will also get higher current density also. What this experiment shows that temperature reduces, current density decreases. And when again as temperature increased, then again the first curve, final curve and first curve is matching. So this graph shows that it is repeatable. So it can be modulated. Your output, if you reduce the temperature, same system can operate at 3000 watt to 2000 watt as temperature will reduce. And it is irreversibly, you can get same reading. So at final 850 degrees Celsius, you reduce to 800, 750. Again, you increase to 850. So the final, initial and final graphs are there. So it is repeatable. The performance is repeatable. So this is for SOFC. So this is our, we have also installed system in the Germany also, Europe also. So this is Hexes system, you can say. This is the water storage. This is the stack in the SOFC. So there will be in Jalgaon, the production plant will soon we will start it. So this is the machinery is required to fuel cell production. So this is a lab result, you can say, yet we are not commercialized it. So we are getting efficiency about 59%. Da Vinci is the name of the product. So there are small scale or medium scale, you can say, technologies are there. In demulsification of formulation oil, this whatever waste heat from the hexes can be utilized in the demulsification plant. As of now, they are burning natural gas to demulsify. But if you use that natural gas into the solid oxide fuel cell, you will get electricity also, and you will also heat the demulsification. They require 50-55 degrees Celsius for demulsification. So there are many applications, you can say solar concentrator is there. You can make steam. put into the SOEC. So the net hydrogen cost might come down, right? So the many concepts are there. We are also writing proposals, but and many institutes, many organizations globally working on this for how to reduce hydrogen cost. So diesel is also not bad until unless you do not pollute. If you can break the diesel and you get syngas, and if your overall efficiency is good, and not producing CO2 the way it is producing in the IC engine, then diesel can be the replaceable fuel. So what we are saying, diesel is not dirty. If we can handle CO2 properly, diesel is also promising fuel in future for SOFC. So there are many technology, operating temperature, paint fuel cell. So solid oxide can go up to 60%, reliable. It is at high temperature. And this is waste process gas energy. Suppose this is the waste gas where methane is available. So you might have seen the refineries. They are burning this, flaring this. So instead of this flaring, you can use it in SOFC. So it will produce electricity also, and parallelly it will emit less heat to the atmosphere. And also it will give electricity because this flaring is continuous 24/7. So this is the point we can address. So there is in telecom cover, there is SOFC or SOEC application in telecom. You can replace the batteries. At military application, there are certain military applications. There is a range extender. Suppose there are some vehicles with electrical, they are going 300, 400 kilometer. If we are hydrogen, it can go up to 700, 800 kilometer. When it is driving, it will generate electricity and it will charge battery or give power to the BLDC motor. So as of now, we have filed 12, now it is 18. Patents has been licensed and 8 has been granted. So we are also analyzed many microgrid. So we are also making scaling units costing 4 or 5 lakh rupees, where you can demonstrate electrolyzer, you can demonstrate fuel cell, and this is safe one. This is with CE certified electrolyzers and fuel cells that we are also doing some microgrid. So we have given to IIT Chennai, Germany, in Ahmedabad, L&T. So these are our customers, NTPC, Jain Irrigation, Oil India, HPCL is also there. So we are also doing some calculations for safety. What will happen if it explodes? What should be norms? So there are scope also to take theoretical projects, implementation in prediction. Yes. Is there any question? Is there any question? Can you see this slide also? E-fuels, hydrogen, and electricity slide. So for electricity, you can go 405 kilometers. So travel distance is 150 to 200 kilometers. It is good. But for hydrogen, it can go 173 kilometers. But for heavy vehicles, it makes sense. Hydrogen, like as a trucks, high distance 600 kilometers per hour per day, 800 kilometers per day, and also loading capacity is high. Then hydrogen vehicles make a sense. So there are incentive scheme from green hydrogen production from Imanari. Notifications are there. So then many electrolyzers are there. So storage of hydrogen is different topic. We will not touch today storage of hydrogen. And I will stop here. I will conclude my talk and I will stop here. Please. Any questions? Hello, sir. Presentation is over. Hope it was aligned with your talk or your FDP, sir. Whatever I have. Yes, sir. It was aligned. Yeah. Yes. Yeah.
Audience are staying in messages, sir. Prashant sir has,
Okay. I will
Prashant
stop.
sir has said nice presentation. He has given feedback.
1 meter, very chat. Okay. So, Prashant, nice prediction, sir. Sir, I am working on it. Okay, got it, sir. So I stay in Pune. I am graduated from Walchand College of Engineering, Sangli. So I know Kolhapur. My brother is MBBS from that Khanvilkar sir का कौन सा government college था उस time नया था तो he is MBBS from Kolhapur Government College. So I know Kolhapur, Panala, and it is close to my heart. When I got that I have to speak with Kolhapur. There are many friends of my good friends in Kolhapur. Kaneri Mutt है ना उधर. So thanks for listening me. Thanks for giving opportunity. And but I will assure you, please, as earliest come in this AI in hydrogen or hydrogen field overall. I think next 20-30 years will be governed by R&D in the hydrogen field. A lot of investment is coming globally in private, from government in this field.
Very informative, and the industry exposure and technologies you showed was very helpful for this topic as well as for us.
Okay, sir. Thank you for opportunity. Thank you for listening me. Thank you. So can we stop here then? Shall I leave?